Yes. So I am hitting exposure,
Very good. Okay. And
both
this is the
sides.
second one. In between, was there a sky?
This is the second one. We started with the sky.
Oh, we started with a sky. I see. Sorry. Okay. One more person is joining. Since we have a long set of exposures going, Elisa and Rohit, would you mind introducing yourselves to the group? It's a small group, so I would want it to go around the room.
Sure, I can start. So, hi everyone. I am Elisa Toloba. I am a professor of physics and astronomy at University of the Pacific in California. Yeah,
Thank you, Elisa.
sure.
I'm
So
Heather Hurd. Oh, sorry.
Go ahead, Heather.
a second, I'm trying helping someone to connect.
Okay, no problem. Go ahead, Heather, please.
Sorry. I'm Heather Hirschley. I'm up on the summit of Mauna Kea. I'm currently operating the Keck II telescope, moving it around and getting it to where they want it for science.
Of all the people on this Zoom call, you're the only one physically at the telescope on the mountain. Elisa's in California. I'm in Hawaii, but I'm at sea level. And Eric is going to join from Arizona later. This is one of the beautiful things about astronomy today is you're operating the world's most powerful, biggest telescope, one person, but hopefully with support from us a little bit to guide the night. Thanks. Thank you, Heather. Thanks for what you're doing. Let's see, who do we go to next? Rohit, do you have a moment to introduce yourself? Maybe Rohit is occupied. Shreya, feel free to introduce yourself.
My name is Shreya. I'm from India, city of Bihar, Muzaffarpur, and I'm in 11th grade pursuing PCB. And yeah.
And you're studying in school, you're studying physics, chemistry, and biology, you said, right?
Yes.
So we use a lot of physics, of course, for this experiment. Some
Yes.
chemistry principles, a lot of math, engineering as well.
Yeah.
But thank you for connecting. What time is it for you now? Is it, let's see. Thanks, Shreya. Rohit, if you have a moment, please introduce yourself. But I think Rohit is helping one of the other students connect. That's why. Go ahead, Rohit.
Yeah, hello everyone. I'm Rohit. I'm a senior, finally an undergraduate student at GuhaThakurta College, Pennsylvania, and I'm studying physics, astrophysics. I have been doing research from over 2.5 years with Professor Raja on Wolf-Rayet star in M33 Triangulum, and also a project on Andromeda Galaxy, of kinematics of Andromeda Galaxy. And yeah, I help in STS sessions also.
And Shreya is Rohit's cousin from the same, close to the same place. All right. So we are studying this galaxy whose image you will see here. This looks like does look like much. It looks like the edge of the moon. It's not actually. This, the fact that it's bright and dark here has to do with the instrument, not with the sky. In fact, this is the full view. You can see it's dark in the middle, bright at the edge, and it has to do with how the camera that's showing this image, how light is being diverted along other paths, right? That's my understanding of why it's dark in the middle. It's light is going somewhere else, not into the camera. But you can see individual stars here, like that dot and this dot. These are actual stars. And if you draw a rectangle over here, you see the small part of this, that's what you're seeing up here, you see. And what we are studying is an even smaller part. The blue rectangle is what we are studying. We are studying these very faint galaxies called ultra-diffuse galaxies. And Rohit has created a very nice podcast about them. Rohit, were you trying to help Hanshika connect?
Yes.
We'd love to get an introduction from you, Aristo, if you are able to. Otherwise, Hanshika, please unmute and introduce yourself. There's Carlos. Carlos is just joining our group. Hanshika, go ahead, please unmute and introduce yourself. Hey, Carlos. Carlos, we're just going around the room doing introductions. Maybe I'll hand it to you to introduce yourself. You're
Yeah.
about to go fly planes.
Yeah. That's my other life, but the one I am living now is a little bit farther away from the atmosphere. Yes, I'm Carlos Alvarez. I'm one of the Keck Observatory staff astronomers, one of the 10 staff astronomers. So my job here is to support the observations that Raja and Elisa are doing today. This is one of the instruments that I support out of the 10 instruments that we have at the observatory, but I'm not really an expert on it. I'm the instrument scientist of 2 other instruments that one of them was used earlier tonight, and another one that has not been used tonight. And I have been working at the observatory for the Keck Observatory for the last 9.5 years.
You will be very badly missed. I know I don't speak alone when I say that.
Yeah, I'm crying already.
Oh,
Yeah, I have to share both things, both
of course.
interests, astronomy and aviation somehow. So this is the way I found how to do it.
Hanshika, did you want to introduce yourself? Are you able to unmute? The time at which we are doing our STS session, which is like 1 a.m. in Hawaii, 3 a.m. in California, 6 a.m. on the East Coast, is not great for Hawaiian students or mainland students, but it's great for India. It's in the late afternoon. It's 4:30 in the afternoon in India. And pretty convenient in the rest of Asia and Africa, Europe.
Few of the coaching students are connected through Hansika, like that phone.
Oh, fantastic. That's very good. Okay. Carlos, Rohit has been using Notebook LM to create podcasts about this program, about this project.
Oh.
And it's amazing when we have a gap in our, let's see, how are we doing with our exposures? We're almost done with this. So when we start the sky frame, I'll play it for you. It's really incredible. I'm learning a lot from these podcasts about our own program because it's a very nice summary. The students from the coaching center are in the same connection as Hanshika. Is your mom there as well?
Yeah, they're connected through phone, so
Okay. They're connected through a phone. Okay. But they probably can hear and see the screen.
yes.
Okay. Rohit, your mom must be so proud of you, rightly. That you're, in fact, both projects you're doing involve this telescope. The Andromeda and Triangulum projects involve this telescope, different spectrograph, but this very telescope, Keck II. Okay, so we're getting ready to start a sky frame, right, Elise?
Yeah,
In 5 minutes, less
minutes.
than 5 minutes.
Couple of minutes.
So for our guests today, what Elisa and one of our colleagues, Eric, another colleague, Laura, and I, what we are studying, and others, we're a big team. We are trying to understand these galaxies. A galaxy is a collection of stars, but these very unusual galaxies where the light is very spread out in the galaxy. The brightness per unit area is very low. Overall brightness is maybe normal, but normally galaxies obey a relation. That is, the more stars they contain, the bigger they are. These galaxies are very big for the number of stars they contain. So normally there's a correlation, right? The more stars a galaxy contains, the bigger the configuration. For the number of stars these galaxies contain, they're larger than typical. So that's why they're called ultra-diffuse galaxies, UDGs. They are bigger than other galaxies of the same luminosity, that is, same number of stars. And they're quite mysterious. It's possible that not all ultra-diffuse galaxies form in the same way. One of the things one tries to understand about galaxies is how much dark matter they contain, which is material that's not in the form of stars or gas or dust. We don't understand dark matter, but we can measure how much there is. And that's one of the things we're trying to measure tonight, is how much dark matter is in this particular ultra-diffuse galaxy. These are so difficult to see and study. Let me see if Jamaica posted something on Facebook. Let me try to bring up that post. It's really beautiful. Let me see if I can bring it up. Not a picture of dogs, but let's see. Jamaica had a nice post somewhere. Where did... There we go. Just go back for a second. So galaxies so faint, they're almost invisible. Ghostly giants. So you can see that they're very diffuse. This is one of the ultra-diffuse galaxies. This is another one. This one is also very diffuse. This one has a bright star, but it's quite diffuse. Is there a way to stop this? What do you call them? This is a...
I think you just do click on the story.
On the story itself, yeah. Okay, let's see, where did it go? There we go, it's paused. No, let me pause it. Yeah, now it's paused. So I'll give you some time to read it. Some galaxies are bright and full of stars, but what about ones that barely glow? This was written by, I think, either Jamaica or one of Jamaica's assistant, Alan, who helps with the social media posts.
Heather, I am ready to move the offset again. Whenever you tell me.
Elisa is going to change
I've stopped guiding.
the pointing of the telescope.
Can I move?
Yes, I've stopped guiding. You can move.
Okay, applied.
Elisa, which window are you moving in control 0?
Oh, sorry, brother, what was that?
Where are you doing the move? Is it in control 0?
In control 0, yes.
Okay. The upper window, right?
I run the command.
In the upper extreme, right? Yesterday it was the lower extreme, today it's the upper extreme.
Sorry, I'm changing numbers.
Oh, no problem, no worries.
Heather, can I expose?
You're good to go, it looks like.
Okay, thank you. I'm exposure.
Thank you.
Raya, what was that? Yeah, sorry.
Oh, is this the window? This
Oh,
window
that is where I run the
Yeah.
east and north.
Okay. Yesterday this was
offset.
the
Yeah,
lower of
that's
the
the
two
one.
extremes. Today is the higher of the two extremes. Okay. Good. I was confused for a moment. But
That's
we are
the one.
doing a 20 sorry, we're now doing a sky exposure, right? So 10-minute
Mhm.
exposure, 600 seconds. We're pointing at a blank region of the sky just to calibrate. And we're doing 374 is almost 3 minutes. So this is about a 9-minute exposure. This shows you like some bright stars. This is not a comet. This is just some kind of reflected light. Astronomy is very boring. No, it's not.
No, it's not.
It's not. No, I've
It's
been doing it for 40 years. Carlos, it's 40 years since I started grad school.
Wow.
Wow.
40th anniversary.
Almost the same for me.
Sorry?
Almost the same for me.
Almost the same, yeah. It's been
Yeah.
30 years since I started coming to Keck and 40 years since I started doing astronomy.
Wow.
Yeah, I got my
Great.
PhD. I got
Yeah,
my
so
PhD in 2002, so
okay,
it's been quite a while
2002.
too.
Okay. And you were at the IAC in the
I was my PhD was at the University of Leeds in the
oh, at
UK.
Leeds. Okay, okay.
Yeah, and then a postdoc at the Max Planck Institute for Astronomy
In Heidelberg.
in Heidelberg. Yeah, I
Who
was
was
there
your
for
advisor there?
Thomas Henning.
Okay, Thomas Henning. Do you know that Rohit did his study abroad at the University of Leeds
Oh, really? I didn't know that.
last year, right? About a year ago.
Yeah,
Oh.
last year I was in Leeds for a year.
Oh, cool. Yeah, I was there. Yeah, I had a great time there. So yeah, I was there for 4 years. So yeah,
That-
I'm
I
sure the
was
city hasn't changed at all.
I would imagine it's a place that I always want to, at some point I need to go back there. And because I have so many good memories from my time there. And I made good friends. I still keep in touch with some of them from the time when I was doing my PhD there, and there were other PhD students. So
Who
yeah,
was your PhD advisor?
his name is so my thesis was a massive star formation, Melvin, and his last name is Hoare. And yeah, my thesis was on outflows from massive young stellar objects. And it's very interesting because part of my thesis was done was based on data that were taken, speckle imaging data before there was adapted optics, high spatial resolution,
See,
images with the speckle imaging in the infrared, taken with UCURT. And I didn't take those data, and astronomy is such a small world that then many years later I ended up working in Mauna Kea, and I saw the telescope where my data were taken for my thesis for the first time.
beautiful, beautiful.
So that's a kind of full circle thing.
And you studied
Yeah.
young stellar objects, and Rohit is studying Wolf-Rayet stars. They're not unrelated. They're both energetic.
Yeah,
One is very massive, of course, but
there
amazing.
is some similarities, yeah.
But
Both are
Carlos,
different.
you have some connection to the IAC. Did you work there before?
So my connection to the IAC is that I was for nearly 10 years before coming to Keck. I was the support astronomer, one of the support astronomers for the Gran Telescopio Canarias for the GDC.
Which is very
So
similar to Keck, right? It's very
well,
similar to Keck.
yeah, it's kind of a clone. It's
of
a
Keck.
little bit, it's a little bit more modern version of Keck. It has a few improvements with respect to Keck because it was built about 1 decade later than Keck, and
right.
a lot of the design that went into GDC was based on lesson learned from Keck. In fact, there was a lot of collaboration when GDC was being planned and designed between Keck. The GDC staff got a lot of feedback from the Keck staff on the design and the construction of the telescope. So like one of the things that is different, just to point out one of them that I think is probably one of the most significant, is like the system that we use at Keck to correct the shape of each of the individual mirrors every time that there is a segment change, and the curvature of the individual segments need to be adjusted. At Keck, you take the measurements during the night, and then someone has to go and mechanically adjust the warping of each of the individual segments based on the measurements that are taken during the night. And at GTC, that is a control system that does the change of the shape automatically based on the measurement. So you don't need human intervention to change the shape, the curvature of the primary mirror segments. So that's one of the improvements that was inspired by the feedback provided by the Keck.
I see. But the segment size, number of segments, those are the same?
Number of segments is the same, 36 segments. The size is approximately the same. The total area of the effective diameter of the primary mirror for the GDC is slightly bigger, is 10.4 meter, while for Keck is 10.2. So it's just a couple of centimeters. The Keck primary mirror is a couple of centimeters smaller in terms of effective diameter. But the pupil, the telescope pupil on the Keck telescopes is on the primary mirror, while on the GDC is on the secondary mirror, which is undersized because it's more optimized to observe in the infrared. And that makes that the actual collecting area, effective collecting area, when you take into account that the secondary mirror is undersized, I think is slightly smaller for GDC or very similar to Keck. So they are essentially 10-meter class telescopes.
Gotcha. You're saying the outer edges of the primary mirror are vignetted slightly?
So when you project the secondary mirror of the GDC on the primary mirror, the secondary mirror is slightly
small.
And it's slightly smaller, essentially.
Is it's a
The-
circular secondary, right? For both.
No, it's not actually. It follows the same shape as
Oh, I see.
Yeah, so it has the kind of we said like serrated kind of
Edges, yeah,
it follows
serrated
it
edges.
just follows
I
the
see.
shape of the primary mirror. So
The Keck secondary is circular, right?
it is circular. That's correct.
How big
Yeah.
is the Keck secondary and the roughly?
I think
3
it's around
meters?
no, I think it's around 1.2 meters.
1.2, I see. I see.
Yeah. The other difference between the GDC and Keck is that the secondary mirror on the GDC, the substrate, instead of being made of zero-dur with the aluminum coating, is made of beryllium.
Beryllium.
And it's
Wow.
very light. It's only like the actual secondary mirror weighs only like 42 kilograms. And the reason why it's that is because it's actually a chopping secondary mirror, so you can use it to do observations in the mid-infrared. So you can
I
do
see.
chopping. So
Like
it needs
tip
to be
tilt?
very So well, it's the
Chopping.
chopping technique that you use.
So on and off sauce chopping.
Yeah, so you do on off, and you
see.
can do that relatively fast. So you need to have a very small inertial mass to be able to do
Sorry, I'm
the
gonna
chopping.
interrupt.
Yeah.
Sorry.
Heather, I'm ready to move to the offset again.
So Elisa's typing some
Okay,
coordinate
go ahead.
offsets over there.
Okay.
Elisa, my control 0 window may be frozen, so I may close it and reopen.
Okay.
Because you've already typed in the coordinates, but I'm not seeing it.
Okay. Are we ready to expose, Heather?
Waiting for the guide box to happen.
So yes?
No, just a moment.
Okay, okay.
Okay, now you can.
Okay, thank you.
Mhm.
Okay, exposing.
Now I can see it. It had frozen for the last 2 moves. So now we've moved back onto the galaxy and Elisa's doing a longer exposure. Four times 300 is 4 times 5 minutes, 20 minutes on the red side, and on this side it is 22 minutes. 1320 seconds is 22 minutes. I'm very happy that the seeing is so good tonight. 0.6.
Yeah, definitely.
Since we've started a like 22-minute exposure, this might be a good moment. Rohit, Shreya, Anshika, and the students there to explain. Rohit, I'm going to call on you to explain a little bit what is seeing, and feel free to use a combination of Hindi, English to explain. I'm putting you on the spot. It's very early in the morning for you.
Yeah, no, I think I can do it. Yeah, so seeing is basically it makes sense as the word says, seeing how well you can see. So this is like how well the telescopes can see in the sky. And by that I mean when you point the telescope in the sky and roughly the sky, like we have meters and centimeters. So similarly in astronomy we divide sky. So the smallest unit is like arc seconds. So it's a very tiny unit, and So that means how well can you see in that? So if there are two stars which are within, let's say, 1 arc seconds away, but if the seeing is just 1 arc second, we will just see one star. Why? Because you can't zoom in more than that. So both will look like one bright star. But if the seeing is, let's say, 0.5, we will be able to see each of them separately. So I hope that makes.
Through a shower door or a, you know, or a glass window that the glass is corrugated. You don't see a clear picture of them. So that's what the atmosphere does. So ये बताइए आप ठीक से.
Yeah, I don't know how much they can listen. That's why I was
This is
not
a good
thinking.
test for you, not for them. Good test.
जैसे शीशा रहता है और शीशा अगर बाथरूम में या थोड़ी देर में गर्मी ठंडा जब मौसम चेंज होता है शीशा धुंधला हो जाता है और उससे आसपास वही शीशा जिससे सब कुछ साफ दिखता था अब सब धुंधला दिखने लग रहा है या क्लियर नहीं दिख रहा है तो वही एटमॉस्फेरिक ब्लरिंग होता है कि एटमॉस्फेयर स्टार को धुंधला कर देता है और वही जैसे स्टार ट्विंकल ट्विंकल लिटिल स्टार हम लोग सुनते हैं बचपन से और स्टार ट्विंकल कर रहा है पर वो स्टार एक्चुअली ट्विंकल नहीं करता स्टार का लाइट जब आता है क्योंकि एटमॉस्फेयर में हवा और उससे सब कुछ मूव हो रहा है तो स्टार लाइट का जो लाइट है रे है वो फ्लक्चुएट होता रहता है हिलते रहता है अपने जगह से अपने फर्स्ट पाथ से ओरिजिनल पाथ से तो उस कारण से हम लोग कभी ब्राइट और डिम होता हुआ दिखता है करके
Rohit, that's much better. It's not just the movement of the air. Hot and cold air have different densities, different refractive index. So light moves at different speeds in hot and cold air because of that. That coupled with the movement, it's like trying to look at a point of light on the bottom of a swimming pool. Or from inside the water looking at a light outside. It looks like the light is dancing. That's what happens. Anyway, good. This is a good day. One of the things you're experiencing, which I can tell you I've experienced I realize I've been teaching for 47 years. I started teaching in grade 11 when I was Shreya's age, 47 years ago. Every time you try to explain something in a new way, you learn it better yourself. You understand it better yourself. This is something really beautiful about being an educator. You constantly learn. ठीक है. Just say a little bit about galaxies and then we will set you free.
Galaxy is like collection of stars. So बहुत सारा स्टार जैसे एक स्टार दो स्टार आसमान में दिखता है पर कोई कोई अगर बहुत जूम करेंगे अच्छे से देखेंगे तो एक जगह पे बहुत सारा स्टार एक साथ एक दूसरे से कनेक्टेड रहता है ग्रेविटी के थ्रू एक दूसरे को अट्रैक्ट करता है तो एक छोटा सा सिस्टम बन जाता है तो इसका एग्जांपल जैसे कभी धागा से बहुत सारा अगर बहुत सारा बॉल्स वैसे लटका तो सब एक करके बन जाता है एक धागे उठा तो सब कुछ उठ जाता है साथ में और बहुत सारा छोटा सा बॉल्स उससे कनेक्ट रहता है बच्चों लोग खिलौना वैसे रहता है तो वही गैलेक्सी में बहुत सारे स्टार को अगर एक साथ मिला दिया और उसको एक सिस्टम बना दिया जो कि सब एक दूसरे से ग्रेविटी के थ्रू कनेक्टेड है पुल्ड है और तो उसी को गैलेक्सी कहते हैं
And Milky Way galaxy तो आकाश गंगा कहते हैं ना?
Yeah.
So that's like our own galaxy, but there are other galaxies like the Akash Ganga that we are studying today. It's very beautiful, Akash Ganga. Carlos and Elisa, Ganga is the Hindi word for Ganges,
Okay.
which is a famous river in India.
Yeah,
Akash
yeah.
means sky. So it means river of the sky. It's the name for the Milky Way in most Indian languages, in Bengali and Hindi.
Nice.
Beautiful. Yeah.
Very appropriate.
Pretty appropriate. You know, every culture names it after something significant in their own culture, right? So
Mhm.
the use of milk was probably very common in Europe, where Via Lactea, the name was born.
Yeah, and also like what kind of that milky color, isn't it? It's
Yeah.
like when you see it on the sky, it has that
Yeah.
kind of whitish color on the dark background. And then the same idea of it's kind of a path
Path,
in the
yeah.
sky. So in the case
Yeah.
of Europe was like a path, and in India it seems like it's like the river, which is kind of the same sense of things moving from one place to another.
Very much so. In fact, the Greek word for milk is galacto, which is related to lactose, right? Galacto. So the word galaxy actually also means milk.
Yeah.
So we're very arrogant people. We name all galaxies after the appearance of our own.
It's
That's
a
why all
human
galaxies
thing.
are called galaxies.
It is a human thing.
It's a very human thing, yes. Priya and Hanshika and the students who are connected through Hanshika, please feel free to ask questions. Feel free to, if you're seeing lots of screens over here, I'm cycling through them. If you have any questions about why we are doing this, what you're seeing on the screen, feel free to ask us. And amongst us, Heather, Elisa, Carlos, Rohit, and I will do our best to explain. I hope I'm not speaking too fast. And Rohit, thank you for explaining, but also thank you for bringing Shreya and the group from Begusarai to this. It's really great.
No, it's good. It's been a while I explained this, so always go out of practice.
Oh.
So how many hours did you say that you need to put together to be able to see something on these galaxies? Raja or Elisa?
Yeah, so that is a very interesting question. So,
The $1 million question.
and we are, trying to learn it actually. So we used the ETC last year, and the prediction was in 6 hours we would be able to see, low signal to noise, but we would be able to see something with the medium slicer and same grading. However, we observed 4 hours and we see nothing, absolutely nothing. So we changed the strategy and we are getting now the largest slicer to have more light go through.
And
So
lower resolution, right? It's lower spectral
a
resolution.
little bit lower resolution. Yeah, so
Which should help.
yeah, we are going from resolution 12 to 25 in kilometer per second. Yeah, so we are hoping that with last night that we got 2.9 hours, and tonight that we are expecting to get something similar. And the change also in the sky strategy. So now we are getting many more frames of a sky than we did last year to track better its variation. We hope to see something. So that is our hope that in 5.8 hours we can see it. So in each
Okay.
individual exposure, we expect nothing. That's basically.
So this is, they say astronomy is a humbling experience, right? We've gone from saying we want to measure dark matter in a galaxy to saying we want to just see a spectrum. We just want to measure absorption lines. We'll worry about whether we can measure dispersion afterwards. Let's just see if we can measure absorption lines first. That's how I'm looking at it. Let's see what we can measure.
So the thing with these galaxies is that there are a few groups that have tried to observe these kind of extremely faint UDGs uh, before. There are basically two groups, and in total, three papers, or well, four maybe, um, on UDGs with similar surface brightness to this, and every single paper uses a different strategy. And within the same group, they change a strategy from one observation to the next. So I guess that we are still learning how to best use KCWI to observe these galaxies. So basically, for this surface brightness, there are observations of three galaxies in total in the literature. Everything else is significantly higher surface brightness, so they are way brighter than what we are doing here. So what we're doing here is comparable to three published UDGs, and each one of them uses a different um, observing strategy, different configuration, instrumental configuration. So we are still in the learning, yeah, in the learning part of this experiment. Yeah,
It makes sense, isn't it? Because it's a relatively new instrument, so
exactly.
everyone is still trying to learn how to best use it. I'm not surprised either that the exposure time calculator does not give you best
Yeah.
very
So,
accurate.
so the thing is that for the ETC is not taking into account this offset sky, and when you are sky dominated and you are observing below the surface brightness of the sky, the variation of the sky and how you subtract the sky is what matters the most, more than the number of photons that you get. So
Right. It's systematics dominated rather than Poisson
exactly,
statistics.
Yeah.
exactly,
And
exactly,
that's difficult to evaluate with exposure time calculator, isn't it? Because
absolutely.
normally what you do is you kind of scale to lower brightness
Hmm.
sources from observing brighter sources, and you just extrapolate and kind of assume that the theory of how signal to noise ratio changes with brightness and sky brightness,
Hmm.
Yeah.
how it scales works. And as you say, yeah, when
Yeah,
you
and by its
start,
very nature, systematic errors are very difficult to model, to include in an
Yeah,
error model. Very difficult.
Mhm.
yeah.
The other piece of confusion that you alluded to, Elisa, thank you for the very clear explanation. The other piece of confusion here is, galaxies have a scaling relation, like luminosity versus size. Many things lie off the scaling relation by definition, right? Most things are on, but a few things lie off. How far off something lies is a huge, or how you define an ultra-diffuse galaxies is hugely variable across different fields. So what other people call, some groups call ultra-diffuse galaxies, we would say they are close to the edge of being normal. We are studying really extreme systems. Yeah, that's what Elisa was saying, that the really faint ones, there's only like 3 or 4 papers for really these really faint systems. But if you just do a keyword search for UDG, you'll get many more papers, because there's so many other galaxies that people call UDGs, because by their definition it is, but by others' definition, including ours, it's not.
Yeah, so definitions are important and difficult, basically.
So is there any other instrument that you can use, or KCWI is kind of
Muse.
muse in the fidelity?
But the resolution is worse, right?
And it's
This
also pretty far
is
south to be, for a telescope that far to be pointing to Virgo.
Yeah.
okay.
These objects are in Virgo and Coma. Coma is even further north. The Coma is
We have
further north.
used demos though. to target the globular clusters on these galaxies. That is how we are actually here. So for I don't know how many years, 5 years, I think, we observed a bunch of these galaxies with the DEIMOS instrument, targeting the globular clusters on these galaxies. And that is where we found, using the globular clusters, that some of these galaxies, about half of the sample, have huge dark matter, huge velocity dispersions, larger than the lambda CDM, the cosmological model that explains how galaxies form, is larger than what that model can explain. So that's why we are here trying to measure the same dark matter, but with a different tracer instead of globular clusters that are very bright and easier to observe because they are like a million stars that were born together. We are trying to use the diffuse light of the stars, of the individual stars, which is way harder to do. But this very extraordinary finding with DEIMOS needs to be confirmed in an independent way to make sure that we are measuring what we are measuring, and that it's not that the globular clusters behave differently, or they have some contamination. So what we are thinking are globular clusters, not all of them are globular clusters. Yeah, yeah, and that.
Lisa, which year was our first DEIMOS observations for the VCGC project? This is when we joined NGVS, right?
I think it was 2012,
12, I think also fall, right?
and yeah, and
In this,
then
it was spring, and then we went to the NGVS meeting in Hawaii at
in Hawaii.
CFHD, right? That same fall. Do you remember we went for the spring observing run?
Yes,
And then in the fall, they had a team meeting. NGVS had a team meeting in Waimea at CFHD headquarters. You and I had gone to that.
I didn't go then to get
But
data.
this is a good lesson for students that sometimes really difficult projects take a decade, take 10 years.
Oh yeah, the
Sometimes longer.
results were published in 2023, so 11 years later after we started observing.
Wow.
Yeah.
First results.
Well, the first ones were in 2018 that we had 3 galaxies that we could publish, and
Right.
then the full sample in 2023.
It's
And the full
amazing.
sample is 10 galaxies, so we are not talking about large numbers, but these are
Mhm.
difficult observations.
Very difficult observations.
Okay, exposures are about to be complete.
So this exposure is, you see, 4 of 4, almost finished. And this one is also almost finished. Oh, it's already finished. Okay, Elisa, ready to move.
Yeah. Hey, Heather, whenever you tell us, we will move to an offset again.
This is the window in which Elisa issues the
go.
command.
Okay. So offset applied. Go back to sky. Okay. Whenever you tell me, I will start exposing, Heather.
You can begin.
Is it done?
Yes, you can
Okay.
begin.
Okay. Exposing. Thank you.
So this is a blank region of sky near the galaxy that we are taking data. Sorry, Carlos, you were going to say something.
Yeah, well, I was gonna just, I'm curious now that, so these galaxies, so they do have globular clusters. So I don't know why I had this idea that these ultra-diffuse galaxies, they are irregular.
They're
And they
highly variable, their globular cluster content. Some have lots, some have very few for same
and they
luminosity.
and they whether their shapes, like the galaxies themselves, are they irregular or they are spiral or they
No,
are
no, they're very, there's no structure. They're very
okay,
diffuse.
they're irregular. Okay.
Very,
Right,
very
right.
round, completely round.
Round, yeah, yeah,
Oh,
Round,
they are round. Oh,
round
okay.
and red. Yeah,
yeah.
it's
So
like very
they're probably
diffuse rough
spherical.
ellipticals.
So they are spherical,
Probably.
and well, around like
Yeah,
approximately spherical, and then they have like a cloud of globular clusters around them.
correct.
Some of them,
Typically,
yeah.
some.
Some
Yeah.
of them have no globular clusters. Some others have as many globular clusters as galaxies that have like a
Normal.
factor of 10 or 100 more in stellar mass.
Okay.
And the globular cluster distribution generally tends to be more extended than most galaxies, but in UDGs, the starlight is very extended.
Yeah.
Just like the globular clusters.
So how big they are? Are they? I mean, how this one that you are observing, how large is the galaxy? Is
What is
like
the
compared
RE?
to the Milky Way.
What is
It's
the
like,
half-light radius, right? You're asking?
yeah, I guess I'm asking how large is in size compared to something like the Milky Way. It's like
In
bigger,
kiloparsecs?
yeah, or in light years. If it's easier, like 100,000 light years across is the Milky Way.
What is the
Or
angular size? I can calculate.
if you have the distance, you should.
The distance is 16.5 megaparsecs. What is the angular size of these galaxies? Elisa, do you remember?
Around, yeah, between 30 and 50 arc seconds.
Radius.
Yeah, radius, the half-light radius.
So let me do 40 arc seconds and see what the calculation looks like.
40 seconds at what distance?
16.5 megaparsecs.
16.5 megaparsecs.
I get 3 kiloparsecs, which is actually not too different from the exponential scale length of the disk of the Milky Way is, 4.5 kiloparsecs. These things are much less luminous, but they're quite big. Am I doing the math correctly? I think 40 arc seconds at...
It sounds, yeah, sounds accurate.
I got 3 kiloparsecs. 40
3
arc seconds
kiloparsecs.
translates to 3 kiloparsecs, I think.
Yeah, because dwarf galaxies of usually have like 1 kiloparsec, and these
Yeah, or
are
even smaller.
vastly
Sometimes even
larger.
half a kiloparsec, yeah.
So the unit that you use to measure the distance, I mean the size of the galaxy, is not like the Milky Way is about 30 kiloparsec. Oh, diameter, but now we are talking about radius, so it's like
Radius,
15.
Mhm.
Okay, yeah, 15 kiloparsec radius. I see that.
It's true that the Milky Way diameter is, or Milky Way radius is, 8 or 10, but yeah, the Milky Way has so many more stars than these galaxies.
Yeah, that's what makes a difference, isn't it?
Ooh, that group dropped off, Rohit. The Sarai group.
Yeah, the coaching time is over, so
Oh, okay.
evening, yeah.
So that was your mom, Rohit, connecting?
Yeah, my mom and all the students who are in the coaching. So there are like 50 students.
Wow.
Roughly 30 of them are from like 7 to 10 or 11, grade 7 to 11. So they all
Wow.
will, and they have to go back early because after it gets dark, it's not the best for kids to go out. So
No, of course. Nice.
You know, we had a group of girls connecting from Kabul in Afghanistan through a program called OMID, which means hope. Same thing. They had to go home at 5 because the Taliban would get suspicious if we had a gathering of girls in the evening. You know, the Taliban don't want the girls to get educated, so we're having to adjust our session timing so that they weren't staying too late in the community center.
Oh, wow.
Crazy what's
This
going
is
on around the
crazy.
world.
Yeah. Oh my goodness. Very different situations, you see. Very different situations, different countries.
Yeah. Yeah.
Mhm. But this is also a good way to remind us, right? That otherwise I do not learn about all these things in Afghanistan and in India. So
Yeah.
at the end,
No,
this program is also, educating us in the difficulties of the world.
it is. It's reminding us of our privilege.
Oh, definitely. Yeah, so
Nice.
we are ready to apply the offset again.
Sure. Let me stop getting.
Okay,
Great, here we go.
good to go. Okay.
And Elisa, I'm gonna play with the status VNC. It shouldn't affect you. Just let it.
Okay, so I can do
Yeah, you can
one.
continue doing your thing.
Okay.
Just I'm gonna
Yeah,
bring
our
up.
cameras probably show things better right now. The super ones are really good now that the moon went down. Yeah.
Right. They look pretty nice, ours.
Yeah, Heather, tell me when we are ready to expose.
Just waiting for the guide box. Right, you're good.
Okay, thank you. Okay.
Okay, so you have the sky cameras on the status VNC. The Keck.
Thank you.
That's you've got big delay in there.
Sorry?
Your VNC has a big lag. That was a while ago, that web page.
I think I need to refresh it.
Yeah, you're gonna have to. Maybe yes, exit that VNC and
Yeah, that's what I'm doing.
log in again, because just type tel status and you should get it back.
Oh, wow. Beautiful.
Yeah, and if you scroll down a little bit, you have the. So
I
you see
don't
that.
have,
Oh,
I'm in view
I
only
can
mode.
do that. Yeah, I can do that. So you can see. So there are the sky, the camera, the old sky camera on the left, and then you have the camera that are, cameras pointing north, south, east, and west. So
That's so beautiful.
these are the ones pointing south. Talking about the Milky Way. Way.
So the Milky Way there,
It is
Beautiful.
there.
South Camp.
Yeah. And then you can see the snow that Heather was referring to. And all the other
sadly.
all the other telescopes. So
Beautiful.
these are 10.
Look at all the snow.
Yeah. You know what is the time lapse of these images, Heather? It's like a couple of minutes or something like that.
Yeah, it takes one every so many minutes, and then It exposes for a long time in each. That's why you can see anything. The top one, where the telescope in the upper right there, in the up view there.
This one here that I'm pointing with the mouse.
Oh no, I was talking about in the up view there. But also in that one, it would be the top of the upper right one in that one as well. Like one closer to Subaru is Keck one. Subaru is the square looking building in the west cam there.
Yeah. You see my mouse pointer?
So yeah, that's you can see
Yeah.
Keck one to the left there, and then Subaru is that telescope in the back. Are they
So
close? They look
this
kind of like
here
it.
is Keck 1, is the other Keck telescope. And this is Subaru.
Yes, they aren't operating tonight. Interesting.
I
Will we
got
be-
some beautiful images of the summit from Waimea. Let me see if I can show you. Not doggies, but
Oh, very nice.
Subaru, Keck, CFHD.
You can see Gemini is the larger one. Kind of.
This is Gemini.
No, that's CFHT, but Gemini is to the right of that.
This
Yeah.
one,
Operator.
right?
Yeah, yeah.
But Subaru is the one that shines from anywhere on the island. Because of the flat dome.
Yeah,
It looks
it was really
huge.
beautiful.
It
So
always looks huge.
I'm using a new iPhone that allows 25x zoom and has beautiful image stabilization. So
Yeah, that's pretty impressive. You took that with an iPhone.
from Waimea on Sunday.
I wish my cell phone could do those kind of pictures.
Yeah, right.
And like Kilauea is not, it's kind of calmed down for a bit. Otherwise, the south cam, you'd see a little bit of the glow, but
Mm.
it's currently, there's a glow in their webcams at the volcano, but it's, all of it's below the surface right now. But when it's really spouting up, you can see it in the south cam between, which one is that one?
Between the two that you see on the south
Mm.
cam.
Yeah, usually it's usually between that Pu'u and the one leading up to the ridge there. But
I guess even 2 days ago it was very active, right?
oh
Kilauea?
yeah, it goes up and down. Like it has a little like a quiescent point where it just calms for a moment and then it builds up and then it starts shooting up again for about a couple half a day to a day or something, and then it calms down again. So we're just kind of in one of those calm moments right now. They've seen that kind of activity in the past, so this is kind of normal.
I think those two telescopes, either in the south cam are UCURT to
Yeah.
the right, and then the UH88 inches to the left.
There might be smaller. Did they take down the smaller UH one? Because that might actually be the other one. In the
They
south.
took that one out. It's not
that's
there
right.
anymore.
Oh my
The
God.
ridge is flat right now.
Oh my gosh, I forgot that.
Yeah, so that's
My brain
got to be.
inserts it there all the time. I don't even notice.
Yeah, so that's got to be UCURT. It's the
Yeah.
one that is more to the,
Yeah.
I guess, east, no, west. Or...
Kind of neat thing is earlier in the month, it's very rare to see you have to catch it kind of this time of year at the right time, but my coworker Matt got a picture of the a little bit of the large melagenic cloud. I can never pronounce that up here.
Magellan Cloud.
Yeah, it's I have no oxygen up here, but yeah, he got a little bit of the LMC over the horizon. You can
Oh.
barely catch it over the flank of Mauna Loa, just past the Pu'u there. Just it's really close horizon, so it has to be like no clouds down there, and he just managed to catch it just right. It was like, oh, that's so cool.
So cool, yeah. Wow.
Its declination is minus 60 something, 68,
Yep.
69.
You can just barely see it over the horizon in the
Wow.
winter if the weather's perfect, or if you're down at South Point, or up here pretty much. Otherwise, yeah,
Oh.
you're not gonna catch it.
I didn't even know that you could see it from here.
Apparently, very barely. And I looked at his picture and I compared it. I was like, yeah, that's it. You got it. You can see where the tarantula
So-
nest is and everything.
Tarantula, yeah.
So the southernmost tip of India is at +6 degrees north, and there are telescopes that are not too far from there, so 10 degrees north. They were doing spectroscopy of the LMC supernova 1987A.
That's so cool.
Crazy. It
Nice.
was, it matters where the trees are relative to your observatory.
It's so cool. That's really awesome. Always like the story that's told that someone going outside to get a cigarette break and looking up and going, huh, that's not normal, It's not supposed to be that bright.
Ian Shelton, right, was this Canadian
Mhm.
astronomer.
It can surprise you sometimes.
The other thing that you can see on these cameras is actually on the west camera, you can see Orion setting right now.
Getting
So
down
if
to the
I
horizon now.
make it big here, that's Orion. It's just setting. I recognize the Orion. And that's actually what we were observing on the first half of the night. Because it
Yeah.
was the Orion molecular cloud. The OB associations on the Orion molecular cloud.
Yeah, we were catching it as it was getting closer to the NASDAQ.
Hmm. Now it's totally setting. These cameras are very nice. They did a really good job with this.
We could use a few more tweaks. I think some of the refresh speeds could be looked at a little harder.
Uh-huh.
We don't want to catch them up to like Gemini North speed if we can, because their cameras are a little quicker. Sometimes it's harder to see things coming in as easily.
Okay.
'Cause I'm,
Is
I'm
the
will-
image in the upper right a drone photo?
The upper right. What
I
it,
think
oh,
is
I
it
think that's a
plane or-
plane.
yeah, it's a plane photo. I
That's
think.
a plane, yeah.
So it's a static image. It's not refresh.
No, it's actually no, it is a movie.
That fields of view one? No, that's static.
Oh, you mean the upper left? Yeah,
Yeah.
that one is there. That
Upper
one's
upper right
Right,
for me.
right, yeah. Yeah,
No,
that
no,
one. The fields of view image is just to tell us that where
Which
the camera-
telescope is which?
Yeah.
also where each camera's pointing. Like the west one is following that arc of view. The north, the ones marked north follows that arc of view, so that you can
Gotcha.
kind of get an orientation of where where clouds are coming from. Because these are called cloud cams, but I really kind of fog cams. I want to see what rolls up, over the plateaus, so we can close fast enough. Which is why I do want to be a little faster on the refresh if possible. But I know it's kind of hard. These long exposures, I get a lot of trouble reading them out. But the left top image is an all sky cam we have sitting between the domes,
Beautiful.
which was our big exciting thing to get. And that one definitely is a cloud cam. So we can see what's up, you know.
Is that zodiacal light or cloud?
Hmm?
That band across the middle, is that zodiacal light or
I think
cloud?
so. Because there were some clouds earlier, but they're not there now. So that must be,
Looks very
You mean-
linear.
I think
You
it is
mean
examples.
everything around here, or
Yeah. That
No,
does
I'm
follow the
thinking
ecliptic right there.
it. The thing I'm looking at is this line.
Yeah. It is following the ecliptic there. So it could be.
zodiacal light?
Yeah.
Zodiacal light is what I would have guessed. Yeah,
Yeah.
this
see, it's
is
so much-
zodiacal light is dust particles in the plane of the solar system reflecting sunlight.
You can see it a bit with your own eyes towards closer to sunrise and sunset up here, which is really cool.
It is really cool.
It's really awesome. Even without oxygen, you can see it decently.
Without oxygen, you can see lots of things.
That's why some of the laser spotters, we'd have to get them oxygen because they'd start telling me, I see something weird. And what do you see? Oh, this light's moving around like this. I'm like, give that guy some oxygen. I think he's having a little problems here.
What is the oxygen partial pressure on the summit? Is it like 60% of sea level?
Yeah, we're 60% atmosphere up here, so
2/3.
yeah,
Wow.
something like that.
Rohit, I've never been more miserable than when I've been on top of Mauna Kea. Physically.
Get used to it.
Yeah.
We'll be a little more tired tonight because I did have a headquarters shift before this one, so I've been off the summit a little longer than usual.